This video is looking at a little bit of detail about electrophilic addition reactions. So first of all, how do we define an electrophile? Electrophiles are either positively polarised themselves or charged, positively charged in some cases, or they become positively polarised by the presence of that double bond. They accept a pair of electrons from the double bond in order to form a new bond. So electrophiles, we're always talking about reactions with a carbon-carbon double bond. And these reactions that we do at AS level are addition reactions. This is because they occur when substances are reacting with these organic compounds that contain double bonds. And as a new bond can be formed to each carbon atom, there's only one product in the reaction, so there's no need to remove anything from the organic molecule, so it's not a substitution reaction. The first addition reaction that we'll look at is the addition of bromine to a simple alkene such as ethene. And here we can see we form one product, which is 1,2-dibromoethane. So why does this reaction happen, and why does it happen with alkenes so easily? Well, if we have a look in more detail at the structure of that double bond, we can see that it's made up of two different types of bond. In the middle, you've got a normal sigma bond. That's a pair of electrons being shared, as you can see, directly in between the two carbon nuclei. The other two electrons that help to form the double bond are located in p orbitals, which are above and below those carbon atoms you can see. They overlap, and so there is a region of electron density above and below the molecule, and those two regions together, both the above and below, together make up the pi bond in an ethene molecule. This means that above and below the molecule, in that double bond there is a high density of electrons, and because they're not being shared between the two nuclei. So it's a lot of negative charge in one place. When a bromine molecule becomes close to that double bond, it means the electrons in the bromine molecule are going to be pushed away towards the opposite end of the molecule. This therefore induces a dipole across the bromine molecule, which it wouldn't normally have. So the bromine atom that is closest to the double bond will end up with a slight positive charge because the electrons are being pushed away towards the bromine that's furthest away from the bond, and that will become slightly negative. The electrons in the double bond then, one pair of electrons, shown by the blue arrow, is going to be able to move from between the carbons to form a bond between one of the carbons and the bromine atom, which is positively polarised. In order to do this, however, because that bromine already has 8 electrons in its outer shell, you need to break the bond between the two bromine atoms. This happens by electrons in the single bond moving to the negatively polarised bromine. So in the next stage of the reaction, we therefore have an intermediate stage where one of the bromine atoms has been joined to one of the carbon atoms in the double bond. The double bond is no longer there because that pair of electrons is now between that carbon and that bromine. The other carbon, therefore, has lost one of the electrons that it was sharing with the carbon on the left, which means that it's got a positive charge because it's essentially lost an electron. The other bromine, on the other hand, has gained an electron, because if you look at that arrow, both the electrons in between the two bromines have gone to the bromine furthest away from the double bond. So that means it's actually gained an electron that it was previously sharing. So we have a positive carbon, this is called a carbocation, and we have a Br-, a bromide ion. And so that bromide ion can now use its electrons into lone pair to form a bond with the positive carbon. And we get our final product, dibromoethane. Correctly, in fact, 1,2-dibromoethane, just to distinguish it from 1,1-dibromoethane. So that carbocation intermediate forms in the middle of the reaction, where there is one bromine attached, and we end up with the other carbon being positive. Now, before we assumed that the bromide ion was going to join to that carbon. That will only be the case if the only negative ions present are in fact bromide ions. So that would happen if the bromine was dissolved in an organic solvent. If the bromine is dissolved in water though, then there are also hydroxide ions present. And hydroxide is actually much better nucleophile. It's much better at using its lone pair to attach to a carbon atom than the bromide ion is. So in the presence of water, it is the hydroxide ion that actually bonds with the positive carbon in the carbocation intermediate. And the final product is much more likely to be 2-bromoethanol. We say the bromine is on the second carbon because we assume if we have ethanol that the OH group is on the first carbon. We don't have to add symmetrical things like Br2 or Cl2. We can also add molecules such as HCl. They will easily react with alkenes as well. There are very few differences in the mechanism of this reaction. As you can see from the balanced equation, one atom, a hydrogen, is attached to one carbon and a chlorine is attached to the other carbon. The way that the mechanism proceeds with ethene is exactly the same. The only difference is that we do not need to polarise the HCl molecule because it already has a dipole due to the chlorine being more electronegative. So the hydrogen by default will always add first because the hydrogen will be the positively polarised end of the molecule. So that will accept the electron pair from the alkene, breaking the bond to form a chloride ion. The chloride ion will then bond with the carbocation intermediate, and you will make simply chloroethane as opposed to dichloroethane. So that's the case for simple symmetrical alkenes. The only other thing you need to know about electrophilic addition is what happens when the alkene isn't symmetrical. So when the double bond does not have the same thing attached either side. And so with an asymmetrical alkene, we're looking at something like propene, where one of the carbons has another carbon attached and the other doesn't. So here's propene. It has a double bond, and then the carbon on the right, as you can see, has got the third carbon attached to it in the form of a methyl group. The first step of the reaction is of course exactly the same. You're going to open up the double bond, the pair of electrons from the pi bond is going to be donated to the hydrogen because it's positively polarised, and the pair of electrons between the hydrogen and the chlorine are going to go to the chlorine to form a chloride ion. But if we now look, we can see that there are two possibilities for our carbocation intermediate. We could end up with a situation where the hydrogen attaches to the carbon on the left, and the carbon in the centre of the chain of the three carbons becomes positively charged. Alternatively, we could have an intermediate where the hydrogen attaches to the carbon in the centre of the chain, and the positive charge ends up on the end of the chain, on the carbon on the left-hand side. This could give rise then to two different products. If the chlorine attaches in the middle, we get 2-chloropropane. If the chlorine attaches on the left-hand side there, we get 1-chloropropane. So in potential, there's a mixture. In fact, the major product, by far the major product in this reaction, is 2-chloropropane. Very, very little 1-chloropropane forms. And we can explain this by looking at the intermediate that's formed. If 2-chloropropane is the intermediate that forms, that means that this carbocation here, where the positive charge is on the second carbon, must be the most stable cation, rather than having the positive charge at the end of the chain on the first carbon. The reason for this is that methyl groups, or any other carbon-containing groups that are attached to that carbon in the centre, have something called an inductive effect. It means that they're able to push electrons, because carbon isn't very electronegative, towards that central carbon. They can do this much better than hydrogen atoms, because hydrogen atoms obviously only have one electron and they're already sharing it with the carbon. And so that means that secondary carbocations, as shown here, or indeed tertiary carbocations, so if you had another methyl group attached instead of that hydrogen at the top, are much more stable. If they're more stable, they're more likely to form, and so therefore they're more likely to be attacked by that chloride ion, forming secondary and tertiary haloalkanes. Now that you've had a look at electrophilic addition, if you haven't already done so, you should also have a recap on free radical substitution and nucleophilic substitution reactions.